In previous weeks, we have focused on probability theory. In econometrics, what do we use probability theory for? We use probability theory to come up with and to evaluate estimators for parameters in a model. So from today on, we will start talking about estimators. Let me start with a question that I received in the email from one of you guys. This question is how to estimate the lambda in the Poisson lambda distribution or Poisson distribution with arrival rate lambda. To answer this question, let's start with this discussion of what is an estimator. So what do we mean by estimating? Literally, by estimating, we mean guessing, but this is not any old guess. The guess has to be based on information. So it has to be an informed guess. In econometrics, the information is data. So the data comes from observing variables following Poisson distribution lambda. So if you want to know the parameter in the Poisson distribution lambda, you've got to observe variables that follow the Poisson distribution. You observe many variables or observe the Poisson random variable many times and see what their realizations tend to be. And those observations form the data. So based on the data, the information provided by the data, you can come up with an educated guess for your lambda, and that will be estimating lambda. Let's start with a simple example. Suppose that you live in an apartment compound. Behind the apartment compound, there is a large pond in which there are lots of fish. And suppose that you like fishing. And when you are too tired studying, you go to the pond and fish for 30 minutes. So you go there every day and fish for 30 minutes. Sometimes you get 0 fish. Sometimes you get 2 fish. Sometimes you get more fish. So the number of fish that you get in that 30 minutes interval is a random variable. Let's say that is the x variable. And after fishing for a while, you start to wonder what is the distribution of this random variable, especially after you have taken this course. So what is the distribution of this random variable? So suppose that we assume the pond is very large and the fish in the pond all swim randomly everywhere. So fish swim randomly and independently from each other. And each fish will only bite your hook when the fish swims near the hook. When the fish swims near and sees the hook, sees the lure on the hook, and the fish bites the hook. For each fish in the pond, because the pond is very large, the fish swims randomly, so the probability for each fish to see your hook and bite is very small. So lots of fish, large pond. But there are many fishes, so you can still get some fish, even though the probability that each fish bites your hook is small. So when the fish swim independently and each fish gets to your hook with a small probability, and the distribution of the x random variable is reasonably approximated by a Poisson distribution with some arrival rate lambda. Now that logic leads to this conclusion that X follows a Poisson distribution. But logic can only take you so far. Logic does not tell you what the Poisson lambda might be. So how do we get information about the Poisson lambda? Well, first, you're going to have to collect the data. Collect the realizations of X from the Poisson distribution. So to collect the data, what you can do is to count the number of fish that you get every day. So suppose on day 1, you fish for 30 minutes and catch X1 number of fish. So count the number of fishes. So count number of fish that you get. So every day you go there and fish for 30 minutes. So you count the number of fish you get and call that number X1. You do the same thing on day 2 and call that number X2. You do that for 100 days. Now you have collected a sample of 100 observations from the Poisson lambda distribution. So suppose the pond condition is the same every day, and the fish doesn't remember that you have been there, you go there every day. So every day, the distribution of your X variable, the number of fish that you catch, follows a Poisson distribution with the arrival rate lambda. So by doing that for 100 days, you obtain a data set with 100 observations from the Poisson distribution. The data set may also be denoted by xi. I runs from 1 to 100. So if all our assumptions are correct, so every day the pond condition is exactly the same, and the pond is not affected by your fishing there, and the fish does not remember you, then the X variables across the different days are independent from each other, and each of them follow the Poisson lambda distribution. Is a random sample, or in other words, an IID sample from the Poisson lambda distribution. So IID here stands for independent and identically distributed. So IID stands for independent and identically distributed. So all the X variables are independent and identically distributed as Poisson lambda. So now with this data set, how do you estimate lambda? Before discussing the estimation of lambda, I want to first remind you of the frequentist point of view of probability. Let's consider the following probability. Probability that you catch no fish in 30 minutes. Probability that x equals 0. In the frequentist point of view, probability is frequency. Probability is frequency that the event happens in an infinite number of experiments. And in this example, it's in infinite number of fishing trips, the frequency that you catch no fish during the trip. So if probability is frequency in infinite number of trips, if you do have made infinite number of trips, you can calculate the probability by calculating the frequency. Of course, you don't have infinite number of trips. You have not made infinite number of trips. You have made a large number of trips. So it is natural to think that the frequency of x equals 0 in your large number of trips is a good estimator for the frequency in infinite number of trips. So that's the frequency of x equals 0 in your 100 trips, which can be written as this: sample average is a natural estimator of the frequency in infinite number of trips, which is the probability. So let me explain this notation a little bit. So this is a sample average of this dummy variable. The dummy variable defined by the event xi equals 0. This sample average of the dummy variable can be viewed in another way. It is also the frequency that x equals 0. Why so? This is because this sum is the number of trips on which you caught no fish, and n is the number of total trips you made. So this is the frequency that you catch no fish on the trip. So this sample average is a natural estimator of the probability because the probability is the frequency of the event in infinite number of trials. Also recall that the dummy variable defined by the event x equals 0, this dummy variable that equals 1 if xi equals 0 and equals 0 otherwise, this dummy variable follows a Bernoulli distribution. So all dummy variables follow Bernoulli distributions and follow the Bernoulli p distribution, where the p is the probability that the event happens. So probability p x equals 0. So this x is a generic notation for this Poisson lambda distribution, a random variable following the Poisson lambda distribution. This xi is a random draw from the Poisson distribution. So it is the number of fish you catch on your ith trip. So this is the ith observation from a Poisson lambda distribution. Because both are random variables following the Poisson lambda distribution, they have the same distribution. Okay, so this dummy random variable follows the Bernoulli distribution with success rate p x equals 0. For Bernoulli distributions, we know expected value of the dummy variable. Expected value of the dummy variable equals the success rate. So what that says is, if we put these two pieces together, we see that The sample average of the dummy random variable is a natural estimator of the expectation of the dummy random variable. In other words, sample average is a natural estimator of population expectation. So sample average is this, population expectation is this. So notice that we are not saying sample average is the only estimator for the population expectation, but it is a natural estimator. So it's a natural estimator. It's well motivated. Natural means well motivated. It's reasonable. It's an estimator that is based on reason. It's based on our view of probability. Our view of probability is that the probability is a frequency from infinite number of trials. We do not have infinite number of trials. We have n number of trials. So the frequency in that n number of trials must be a reasonable estimator for the frequency in infinite number of trials. So based on this deduction, we can say that sample average is a reasonable estimator for population expectation. This is the case. This statement seems to be well motivated when the random variable considered is a dummy random variable. It is, in fact, a good principle to use to come up with estimators for general random variables. And when we use this principle, that's called a sample analog principle. For general random variable x following some distribution, if we have an IID sample from this distribution, then the sample average, the average in the sample, which is the average of, which is denoted xn bar, which is the average of the observations in the IID sample. That is a sample analog of sample analog estimator of the expectation of x, because in the frequentist point of view, expectation is the average of the value of x when you conduct the experiment infinite number of times and therefore observe x infinite number of times. And if expectation is that average from infinite number of trials, then the average from finite number of trials is a reasonable estimator for that expectation. So using sample average to estimate population expectation is called the sample analog principle. And the sample average is a sample analog estimator for the expectation. And this sample analog principle is very helpful for coming up with estimators. So we're saying that sample analog principle is useful for coming up with estimators. What we are not saying, I want to stress, is that sample analog estimator is not always the best estimator. So we might run into talk about some examples later on, but we may not. But I want to stress that sample analog principle is a useful principle, but it doesn't always generate the best estimator. Although it does not always generate best estimator. And one problem or one feature of using the sample analog principle is that you can use the sample analog principle to come up with different estimators for the same parameter. So all the parameters may be based on sample analog principle, just applied on different equations. So we will consider an example like that. So obviously, when different estimators are motivated by the same principle, if there is a ranking among those estimators, then clearly the principle is not always generating the best estimator. It could generate good estimator, it could generate bad estimator. But it's a useful principle to come up with estimators. And the principle is quite simple. Simply use sample average to estimate expectation. Now come back to the Poisson random sample. So this is IID sample from Poisson lambda. Suppose our goal is to estimate lambda. We can recall from the video where we talked about Poisson distribution that expected value of x equals lambda for x that is a Poisson random variable. So lambda is the expected value of x. So by using this equation, by the sample analog principle, we can come up with the following estimator. For estimator, we usually use the parameter with the hat on it. So lambda hat. And this is one estimator, which is based on this expectation formula for the Poisson random variable. So we indicate that by a subscript E. So that's an estimator for lambda based on the expectation of the Poisson distribution. This estimator will be the sample average of x, because we are trying to estimate lambda, and according to equation 1, lambda equals the expectation, and by sample analog principle, we can estimate the population expectation using the sample average. Therefore, a natural estimator, a reasonable estimator, is this estimator, which equals the sample average of x. So we have come up with one estimator for the Poisson lambda. And is this estimator a good estimator? So how do we evaluate the quality of estimator? When do we say an estimator is a good estimator or a bad estimator? Before discussing the quality of estimator, I want to remind you of 2 point of views about events, the ex ante view, ex ante, and the ex post view. In the context of estimation, the ex ante view, ex ante, is before we observe the random sample. So before the random sample is realized, or is before their values are observed. So before their values are observed, these xi's are random variables. So these x1 to xn are n random variables. And because this is a random sample, these n random variables are also independent. They are independent and identically distributed random variables. So whenever we say the random sample is IID, the sample is IID, we're taking an ex ante point of view. And exposed xi, I from 1 to n, so this random sample is observed and it becomes a column in your data set, a column of numbers in your data set. So ex ante, it is random, it's an IID sample. Ex post, after it is observed, it reduces, it's realized as in numbers. So when we evaluate the quality of estimators, we take the ex ante point of view rather than the ex post point of view. Why so? Because ex post, the sample is realized, they are in numbers, and from these in numbers, the estimator that we came up with is a fixed number. Of course, we want the fixed number, which is intended to be a guess of the true value of lambda. We want this to be close to lambda. We want this difference to be small, the absolute value of the difference to be small. But this is a number exposed, and this is the population value, it is a number. So this difference is a fixed number. Is it small? Is it big? We don't know. We do not know whether this is small or not, and there is no base to judge whether this is small or not. The reason is we do not know lambda. So no way, no disciplined way to judge how small this difference is. So exposed is not a very useful point of view for evaluating the quality of the estimator. Well, ex ante, the estimator is still random. And given lambda, we can try to learn about its distribution. And we can evaluate whether the distribution is very spread out, meaning that it can be very different from lambda a lot of the time, or it's concentrated around lambda. And whether the distribution is spread out or concentrated, that is some kind of measure of the quality of the estimator. Clearly, the more concentrated is better than the more spread out distributions. And also, we want the distribution of the estimator to center around lambda. So in expectation, we want the estimator to be correct. And that is also a property that we can evaluate for the estimator. So X and T, we have many disciplined ways to evaluate the estimators. So one disciplined way is to calculate the expectation and see whether the expectation of the estimator is equal to the true value. That is to calculate the bias. So what is the bias? The bias is expected value of the estimator minus the true value. If the bias equals 0, that means on average, the estimator is correct, then the estimator is called an unbiased estimator. So is the sample average an unbiased estimator? Is this an unbiased estimator for lambda? Well, we can try to calculate the expectation. We can try to calculate the expectation. So in this expectation, we have a constant 1 over n times a random variable that is the sum of all the xi's. The constant is non-random, so it comes out of the expectation by the linearity of expectations. So that's 1 over n expected value of the sum. And for those of you who are not very familiar with summation sign, this summation of xi from 1 to n is x1 plus x2 plus until xn. So in our example of the fishing trip, this n is 100. So expected value of sum of random variables equals the sum of the expectations. So that equals expectation of x1 plus expectation of x2 plus plus expectation of xn. And all the expectations are the same because we have a random sample from the Poisson distribution with parameter lambda. So all the xi's are from the Poisson lambda distribution. So this is lambda. This is also lambda. This is also lambda. All of these are lambdas. There are n of them that are added together. So n lambdas added together is n times lambda. And the two n's will cancel out, gives us lambda. So clearly, from this calculation, this sample analog estimator based on the expectation of the Poisson distribution is an unbiased estimator. So at least it has this unbiasedness property. So therefore, this is an unbiased estimator. We can also calculate the variance of this estimator to see if this estimator is very variable. If it's too variable, then we have less confidence in it. Then it's more likely that it's very different from the true value. But if it's less variable, then it's more tightly distributed around lambda, which is a good thing. So we can also calculate the variance of this estimator. The variance of this estimator is the variance of the sample average, because this estimator is the sample average. That's the variance of the sample average, and the variance, as you can see, it's the variance of the constant times this random variable. The constant in this multiplicative constant in variance gets put out of the variance after squaring. So that's a property of the variance operator. So that becomes 1 over n squared, variance of the sum. Sum, as I just reminded you, this sum is x1 plus x2 plus xn. Now, variance of sums of random variables is not always sum of the variances. Remember, because there might be covariances among the variables. However, these x variables, they form a random sample, an IID sample, meaning that they are independent from each other. When they are independent, their covariances are zeros. Therefore, for independent x's, the variance of their sum equals the sum of their variances. So the variance of their sum equals the sum of their variances. So this is by IID. The variance of each x, what are these? They're all the same. First of all, they are all the same because all the x follow the Poisson lambda distribution. So it's n times the variance of x for x following the Poisson lambda distribution. One of the n cancels out with this n, therefore that equals 1 over n variance of x. Before plugging in the actual value for the Poisson distribution, we can look at this form of the variance of the estimator. This variance of x, it doesn't change with the sample size, doesn't change with how many trips you made, how much data you collected. But this 1 over n drops with n, drops with the amount of data that you collected. So one useful observation is that The variance of the estimator that's based on the sample average drops with n. It's inversely related to the number of observations. In fact, if you use the limit concept, the limit of the variance equals 0 because the limit of 1 over n is 0. And this part doesn't change with n. This is a good property. This is saying that this estimator utilizes your data very well. When you increase the amount of data, the estimator gets better and better, gets less and less variable. When there is an increased amount of data, the variance of the estimator drops, so decreases. Now let's plug back in the Poisson case. In the Poisson case, the variance of this estimator is actually 1 over n times lambda, which is lambda over n, because the variance of the Poisson distribution is also lambda.